All right, hello guys. Welcome to my fifth video. For this video, I'm actually going to be talking about large language models and continue about what I was talking about in the previous video. So I'll be going into detail about how do the language models actually store their facts and talk a little bit about transformers and going into detail just to give you guys a little quick recap. To get things started, my name is Adrian Flores Aquino. These videos are specifically for my CS 4540 class, also known as Intelligent Agents in Learning Environments. So yeah, let's get into it. I want to talk about the recap just to get you guys familiar with what I'll be talking about in this video. Just in case you guys didn't see my previous video, I pretty much went over about large language models, which are pretty much based on a transformer architecture. So this pretty much means that every sentence that you put in, so this sentence right here says that which does not kill you only makes you and then blank. So pretty much the transformers is pretty much making every word that you see in the sentence into a token, and for those tokens, it is then created into a vector, as you can see right here. And those vectors would actually go through an attention layer, which is when they start communicating between each other. And in that attention layer, they actually start changing their values depending on what the context of the word is. So if you were to write snowy forest, the word forest and the vector corresponding to the word forest would actually change due to the fact that the context of it is saying that it is actually snowing in the forest. So depending on what the context is of the whole sentence, the values do tend to change. And after the attention layer, from there, it actually goes through another layer called multi-layer perceptron, which is what I'll be going into detail in this video, and just talking about how it actually works and the process of it. And pretty much just what it actually does is pretty much ask questions to every vector, asking it could be whether 50 questions, 100 questions, even 1,000 questions to determine what the that corresponding word corresponds to and what it actually means. And this whole process actually keeps repeating until it gets the final layer, which would actually give the final output into being able to predict the next word. So yeah, so I'll be talking about how do large language models actually store facts. So before getting started, like I was saying before, what is a MLP and also known as a multi-layer perceptron? And if you guys have never heard of this word, it's totally fine. This is actually very new to me as well, but it is actually a type of artificial neural network that uses multiple layers of neurons. So what I mean by this is that, as you can see right here, every single neuron corresponds to a single question, and depending on what the neuron corresponds to, as in value wise, it would then change the final output for the prediction. So it actually enables the language model to be trained, and it actually enables the prediction of the next token, meaning by the next word that is has to be predicted. So when it comes to MLP, there is actually a specific structure that corresponds to, which is actually three important components when it comes to the multi-layer perceptron. And those components actually correspond to the matrix multiplication, which actually takes the input layer and multiplies it to a big matrix. It could be hundreds or thousands, depending on how big the data set is. And this pretty much just asks a series of questions to the vector to get to know a little bit better. The second component is actually the ReLU component, also known as the rectified linear unit. And this pretty much just simplifies the vector into being able to give the model a simple yes or no. So instead of asking it so many questions, it would just be simplified so it could be able to give a simple answer or response to make it easier for the model. And then for the final component, it is actually the matrix multiplication again. But in this case, it is actually determining the final result based on the neuron activity. So depending on what neurons are lit up in the middle section, in the middle component, as in the ReLU component, it will then be able to determine what the final output is. And once it reaches the final output would actually be added with the input vector. And then from there, once they are both added, it would actually give the final prediction. So let's talk about a little bit more about the first component, which is actually the matrix multiplication, But in this multiplication, there is actually a bias that is added as well. So let's say you give a sentence, right? The sentence would then be converted into tokens, and then from there, each token is converted into a vector. So the input vector is pretty much just multiplied by a large matrix, like I was saying before. And you could pretty much think of like every column right here to be thought of like every column to be asking a question to the vector, right? So it could be whether you give Michael Jordan, right? Let's say you give the word Michael. It's pretty much just asking that word specifically, like, oh, does he play basketball? When was he born? Is it a man? Is it a woman? Just every type of question that you could think of, it is being asked to the vector to be able to identify it better. And you could also think of each row of the matrix to be considered a direction in the embedding space. So what I mean by this is you could think of like a graph, but in a very complex way. So whether, as you can see, in a 2D graph, it'll just be the y-axis and the x-axis. In the embedding space, it is actually much more complicated due to the fact that there's much more values in the matrix. So it could either be going up, down, middle, curved. It all depends on what the value actually is. And once it has actually been multiplied with the vector, it would give a value here. But before getting the actual final value, it is actually going to be added with a bias. So that's pretty much done after the multiplication. And it's pretty much just to uh, be able to like standardize the actual value so it doesn't go too far or doesn't get too big, in other words. So as you can see, there's actually big words here, right? So negative 199, negative 177, 118. But in reality, that isn't what we want. We actually want to simplify those numbers into much smaller numbers. So this is where the rectified linear unit function comes into play. So this is pretty much just applied to the results of the matrix multiplication. And once it actually converts the bigger numbers into small numbers, this is where we actually convert the negative numbers into zeros and we leave the positive numbers just how they are. So this pretty much just allows us to ensure we are giving a clear yes or no signal between every components, every process of the component. It's pretty much similar to each neuron being lit up in a neural network. So what I mean by this is that once this has been converted into zero or just leaving it as they are, if they are positive, you could kind of think of it as a neural network with the neurons. So since it's one, realistically, the neuron would be like super bright. But if it's zero, the neuron would be super dark, meaning that it pretty much has no effect to the final output. So you kind of think of it that way. And in the graph, when it comes to graphing it, it would look something like this due to the fact that the negative values are all zeros and then the positives, they are left just how they are. So it just keeps going up. And for the final component, it's actually matrix multiplication again. But in this case, we are actually figuring out the output. So the results of the ReLU function is then multiplied again by another matrix, like in the first component. And this pretty much allows it to return to the original embedding space, meaning that instead of just being simplified again, it'll come back to the real numbers. And you can kind of think of every column to be thought of as a direction in the embedding space. So it pretty much just determines what features to add in the final result. So let's say this one is a positive number, right? And it isn't zero. Okay, that one's checked off, right? This one's negative, so it's zero. Okay, that one doesn't apply. But if it does apply, let's say, like I said before, you're giving the word Michael Jordan. So let's say the first word is Michael, right? This one checks off, so it's saying, okay, Michael does play basketball. This one is Michael's not a woman, and then this one's checked off, so it's Michael was is the owner of the word brand Jordan, right? So that's just an example, right? And with this case, for the final output, with the matrix being multiplied with the vector, it is actually added to a bias again, and the final result would actually be added to the original input vector as well. And from there, it actually predicts the final output. So like I was saying before, this is the input layer that is added onto the final output, which would be this over here. And then once they have both been added, that pretty much means that it is now able to predict the right word for the upcoming token. So now let's talk about transformers. This is just kind of going over about what I talked about before in some other videos, but I'm gonna just be going into some details that maybe I might have missed in the previous videos. So when it comes to tokens, adjectives and the nouns are very important to being able to, I guess you could say, predict what the word might be. So the goal of the transformers is to have nouns updated by the adjectives. So this design actually is able to keep everything parallelizable, meaning that things should be inferable from the state of the vector itself, no matter the order. So like I was saying, the adjectives and nouns do have a important impact on the word. So like creature right here. When you think of the word creature, you could think about any other creature like I don't know, like a giant, a monster, um, a dragon, just anything related to a creature, right? So it's pretty much just in general. But when it comes to the adjectives, you are saying fluffy and blue. So these adjectives pretty much do have an impact on the word that comes after it. So this is why you get a picture of a fluffy blue creature, right? And same goes for forest. When you think of a forest, it could be snowy, sunny, burnt, anything you could think of. It's pretty much in general, right? But when you give the word verdant, you are now thinking of like a very green forest, like with lots of plants, trees. You kind of think of it that way, right? So the adjectives do have an important impact when it comes to the upcoming words. So let's talk about the query matrix. There are actually three types of matrices that you have to be in keep in mind for. So it's the query matrix, the key matrix, and the attention pattern, or also known as the yeah. So just the query matrix, the key matrix, and the dot product, which is the I believe it's the final matrix. Um, so for the query matrix, it allows each word to ask a question. So kind of like in the first section that I was talking about, the previous words are able to ask questions. So like it says right here, the query matrix allows each word to ask a question. Like for example, is there any adjectives in front of me, right? So that pretty much changes the actual value of the word. The word asking is then associated with the new smaller query vector, and the query vector actually encodes the idea of looking for an objective, an adjective, and then there's the key matrix. This pretty much is that the key matrix gives adjectives the capacity to respond numerically or um, mathematically. This is a typo, so just ignore that. The matrix is then multiplied by the embeddings to produce a sequence of keys, and the keys and queries are trained together, which allows the key matrix to output simple answers like yes or no answers, like in the first section. And this is where you get the dot product, which pretty much gives a grid of the values that tells which words are relevant to updating others. And this is where we start getting into the attention pattern, which is where we want to actually determine which values do matter the most. As you can see right here, the big ones are the ones that matter the most. And this is pretty much just like a weighted sum of every value and vector. But we don't want them this big, which is where softmax comes into play. The softmax pretty much allows it so that the large numbers correspond to a larger weight in the output and allows there to be a smooth change in the output since it acts like maximizing the function. So like the big numbers would then be coming into small numbers, and in the end, all the small numbers that are converted will then all add up to one, which is what we actually want. And there's one important thing to remember, it's about masking. When it comes to sentences, we actually don't want the previous words to have other effects on the future words. So when it comes to masking, we actually make some of the values um, zero. So when it comes to calculating the actual prediction, the previous words that we already checked, we don't want it to have any effect on the future ones. So when it comes to making them into zeros, they are pretty much just being masked, so just hidden. And yeah. Thank you for watching my video. I hope you guys learned something. I know it's kind of a loss since I do have only 15 minutes to talk about it, but yeah, I'm glad you guys enjoyed it. Thank you.